Okay, we need to finish those last two examples in section 8.8 on improper integrals. And so the very last example, and we skipped one, we'll have to go back to. So this example is the integral from 0 to 2 of 1 over the cube root of x minus 1 dx. And again, if you don't look closely, you just think, well, this is one maybe you would have done in Calc 1. But notice the problem here is, on the interval 0 to 2, 1 makes the function undefined, so there's a problem here. And remember, just because a number makes a function undefined doesn't mean there's a vertical asymptote there. It could just be a hole in the graph. But one here, this is a vertical asymptote, so it is an improper integral. So since the discontinuity, the infinite discontinuity is at 1, we need to break this integral up into the integral from 0 to 1 of 1 over the cube root of x minus 1 dx plus the integral from 1 to 2 of the same thing. Okay, so remember when we defined the how to deal with the infinite discontinuities, we wanted the infinite discontinuity at the endpoints. So it's at the endpoint here and the endpoint here. Right? So to see if this integral converges or diverges, we need to work these two out. Now, if we work this first one out and it turns out to be, and this diverges, there's nothing left to do. You don't have to do this one, the whole thing will diverge. Remember, the only way the original integral converges is if both of these converge. So if you work one out and it diverges, you know the original one diverges. Okay, so let's just do this first one here, the integral from 0 to 1. Since we're going to integrate this, let me rewrite this not as a quotient. That's x minus 1 to the minus 1/3 dx. I'm just kind of looking ahead. Now remember, our infinite discontinuity here is at 1, so I'm going to, the definition says rewrite as a limit. So it's the limit as c approaches 1 from the left. So you imagine you're choosing a c in between 0 and 1, which means c is going to approach 1 from the left of the integral from 0 to c of x minus 1 to the minus 1/3. So again here, imagine the interval 0 and 1. We have an infinite discontinuity at 1, a vertical asymptote. So you choose a value c in between 0 and 1 and integrate from 0 to c. We're assuming, the function's continuous from 0 to c, so this integral will exist if c is less than 1, and then you take the limit as c approaches 1 coming from the left. Again, if you draw a little interval and imagine where the vertical asymptote is, you can figure out what that term is going to be. Okay, so let's do the work. Now, this is a linear substitution, right? If you let u be x minus 1, you know you can integrate u to the minus 1/3, and x minus 1's linear, so I don't have to work that out. So what's the integral of just plain old x? Don't worry about the linear part. The integral of x to the minus 1/3, you add 1 to the exponent, divide by the exponent, so that's x to the 2/3 over 2/3. So what is linear to the minus 1/3? It's linear to the 2/3 over 2/3. Okay, so let me write limit again. Okay, so the integral of linear to the minus 1/3 is the linear, add 1 to the power, to the 2/3 over 2/3. And again, you have to adjust for the slope with the linear substitution, but the slope is 1, so it's 1 over 1, so we don't have to do that. And we're going to evaluate that from, what is this one doing? 0 to c. So now it's just a matter of doing some simplifying there. So we have the limit as c goes to 1 from the left. If you invert and multiply, I get 3/2. Well, let me just write it out. 3/2 x minus 1 to the 2/3 from 0 to c. I could have done that on that step. I don't know why I didn't. And now let's plug in our endpoints. Keep writing limit until you take the limit. So if I plug in c, I get 3/2 c minus 1 to the 2/3. And then minus, when you plug in 0 for x, negative 1 to the 2/3. Remember, 2/3 means cube root squared or squared cube root. So if I plug in 0, I get negative 1. The cube root of negative 1 is negative 1 squared is 1. So I just get the 3/2. Well, this limit's easy to do. We don't, I put 3 over 3. We don't need L'Hopital's rule or anything here, because when c approaches 1, that's heading to 0. And we don't have a problem with undefined, right? Because if you plug in a number less than 1, like 0.99, yeah, that's negative, but you're taking the cube root of a negative and then squaring it, so that's no problem. So it looks like what we're getting here is negative 3/2, aren't we? So this first integral, this first one here, this improper integral, is converging. All right, now we have to do it again with this one. All right, I'm going to take the liberty that I've already written this out, and I will try to talk slowly because you're going to want to rewrite it underneath in your notes. So now we need to do this problem, okay? So I'm going to change my endpoints from 1 to 2. Notice the integrand is the same, right? The integrand is the same. So we're going from 1 to 2, and let me change this from 1 to 2. But this is going to be different, isn't it? Okay, so now imagine the interval from 1 to 2, and again, 1 is where the vertical asymptote is, and so now we're choosing a C between 1 and 2, so C is going to approach something. C has to approach 1, C approaches 1, but this time we're coming from the right. Right? And again, sorry, not 1, C. Okay? So now when we choose this C between 1 and 2, the integral from C to 2 has no discontinuities there, it's continuous, so that integral is going to exist, right? This integral is going to exist. It's just when you take the limit as C goes to 1 from the right, is that answer going to exist? So, so you can integrate that and then move C and integrate that and move C and integrate that. These keep giving you answers, but as you get closer to 1, is that blowing up or not? Okay, so notice this step is exactly the same, except for I have to change the endpoints, right? From C to 2, and this is the right. Right, the integration step is exactly the same. And then this is exactly the same, because all I did was flip the 2/3 to be 3/2. So this is C approaching 1 from the right, and this is C and this. Again, in your notes, you should be writing all this down. I'm kind of taking advantage of the situation that I can easily erase. Okay, and now this is going to be different, isn't it? So let me get rid of this. Okay. So again, of course, you can always pause the video and catch up to here. Okay, so now I need the limit as C approaches 1 to the right. And now I'm plugging in 2, that's 1 to the 2/3, which is 1, so I'm getting 3/2. Minus, and now I need to plug in C. So it's 3/2, C minus 1 to the 2/3. Let me check my work here. So I plugged in 2, that gives me 1 to the 2/3 is 1 times 3/2 is 3/2. And then when I plug in C, I get that. And now it's just a matter of taking the limit again. Well, when C approaches 1 from the right, so you're plugging a number a little bit bigger than 1, so you're taking a positive number to the 2/3, that's not a problem. But when you plug C as 1, you get 0, and notice the answer is 3/2 from here. And so this integral converged to minus 3/2, this integral converged to positive 3/2, and so the integral from 0 to 2 of 1 over the cube root of x to minus 1, dx is 0. You add the two answers together. And therefore the integral converges. Okay. So again, if either one of these had diverged, then my original integral would have diverged. What's irritating is when you work a problem like this, and you work out the first one and you get a number, and then you work out the second one and then it diverges, which means you didn't need to do this first one, but you don't know that ahead of time. You just kind of have to work things out. Okay, so that's that one. So now let's go back and look at that example that was a couple pages before in the notes. And again, it's sort of an anomaly. Well, it's not an anomaly. It's something that you don't expect. Okay. I mentioned some facts here that we need to solve this problem, and we're not going to prove it. We're just going to. I'll draw a picture to convince you that this is true. And we're going to see an idea just like this when we get to series in chapter 9. So I don't mind talking about this similar idea here. It says, let f and g be continuous functions such that 0 is less than or equal to g, which is less than or equal to f. So we're assuming these functions are non-negative, so they don't drop below the x-axis. and we're assuming it's some interval a to infinity. So a could be negative. I'm going to draw a picture. I'm assuming a is positive. Right. So let me draw a picture with this a possible picture. So I'm assuming a is positive. So we're in the first quadrant here. So from a to infinity, this is true. So the functions do not drop below the x. They can touch the x-axis, but they can't drop below. And f is always greater than or equal to g. So let me just draw in some g. Right, whatever. So there's g. And we're only interested from a forever. So here's g of x. And now f of x is bigger than or equal to that on the interval a infinity. So down here, f could do whatever it wants. But from a to infinity, it's no less than g. So suppose f did, I don't know, that and then touched again. And I don't know. So they touch here and they touch here. But f can be equal to g, but it can't drop below. So here's f. Okay. So it says, okay, there's two parts here. If the integral from a to infinity of f of x dx converges, then the integral from a to infinity of g of x converges as well. Now that sort of makes sense, right? Because think about geometrically what we're talking about here. If the integral of f converges, that means the area under f, when you go from 0 to infinity, obviously, both of these graphs have to approach the x-axis, right? Because if this blows up, you're going to have an infinite area, right? So for sure, they have to get closer and closer to the x-axis. The x-axis has to be a horizontal asymptote. But if that integral converges, that means that this is finite area. Well, g has less area because it's always underneath f. So if integral of f converges, the integral of g will have to converge. Okay? So that sort of makes sense from the picture. Now, likewise, what if the integral from a to infinity of g of x diverges? Then it says the integral from a to infinity of f diverges. So suppose the integral from 0 to infinity of g diverges. So think of this area is infinite. Okay, it's getting closer and closer, but it's infinite. Okay. Well, the area of g, the area under f is going to be bigger than the area of g. So if the area under g is infinite, so will the area of f. It'll be infinite as well. Now be careful, you can't mix and match stuff here. For example, suppose you knew the integral of g converged. Notice that's neither one of these hypotheses. Is if the larger one converges, the smaller one converges. If the smaller one diverges, the bigger one diverges. What if you knew g converged? It's not the assumptions on either one of these. Well, f could converge or f could diverge. You don't know. It could do either. Likewise, suppose f diverged, which is not in either hypothesis here. If f diverged, g is smaller, so g could also blow up to infinity, but g could also head to 2. Okay? So if the larger one diverges or the smaller one converges, you don't know what the other one does. Okay? If the if the large one converges, the small one converges. If the small one diverges, the large one diverges. Okay, that's what this is saying. And if you just think about the picture, you can see that. Okay, so now with that fact in mind, we need that. And again, we're going to see the same idea when we get to series in chapter 9. This is an example called Gabriel's horn. It says, look at the graph of f of x is 1 over x for x greater than or equal to 1. Well, we know what that looks like. Right? We're only interested, when x is at least 1, the graph is positive, so we're like this. So we're not concerned about the 1 over x part over here. And we're doing x greater than 1. It says the solid formed by revolving about the x-axis, the unbounded region lying between the graph of this and x equals 1 and the x-axis is called Gabriel's horn. So okay. Now notice it's the solid of revolution. Remember you did that at the end of Calc 1 in chapter 7, right? You take a graph and you revolve. We're revolving about the x-axis, and I cannot draw. I will do my best. So imagine this thing revolving around the x-axis like this, and then it's going to look like that. It's going to make a horn. Okay, that's not great, but it's not bad. Okay, so this is infinite, right? It's from 1 to infinity. It goes on forever. Okay, show this has a solid. Oh well, we want the volume and we want the surface area. Well, remember. From Calc 1, we're going to do this with shells, right? We're gonna do it with shells, right? So imagine a rectangle, all these rectangles, remember doing that? And how do you get the volume, right? When you rotate that around, you get a coin, which I can't draw. Right, you get a coin, right? And notice the radius of the coin was the height of the rectangle, right? And we were doing the volume, what's the volume of the coin? It's pi times the radius square, right? Times the height, but remember the height was the delta x, right? So you got a formula for shells doing that. And so if you do this problem, it's pi from the integral from 1 to infinity, because we're going from 1 to infinity, of the radius squared. Well, the radius is the height of it's your function, so it's 1 over x, whole thing squared, dx. Okay. So again, you can go back and look in your disk method. I maybe said shells earlier. I'm using disk method. Okay. Well, okay. So this is pi integral from 1 to infinity of 1 over x squared dx. Okay. Now we could work this out. This is an improper integral because we have an infinite limit of integration. Take the limit, but we don't have to because we proved a theorem today. Remember the one with the p's. The integral from 1 to infinity, and the 1 was important, of 1 over x to the p here is 2, was 1 over p minus 1. Right? So we already know how to compute this integral. We did it. So pi out front. And this integral right here, right, because we're starting at 1, our theorem started at 1, and p is 2. It's 1 over p minus 1. Right? And so which turns out to be pi. Right? So the volume here, the volume of Gabriel's horn turns out to be pi. So you could, if you could, you could take, a paint can that holds pi gallons and pour it in here and fill it up. Well, I say pi gallons. It's whatever cubic units we're doing here, right? So pi cubic units, you'd fill it up, right? It has a finite volume. Okay, now let's do the problem again. It also says to do the surface area. Let's do the surface area. So remember the surface area we denote by big S, arc length plus little s. I don't know why. And so it's 2 pi, right? Integral from 1 to infinity. Now what was the formula for that? It's the r of x. How far is the curve to the x-axis? Well, that's the height. That's just f of x. So the r of x is f of x. Then times the square root of 1 plus the derivative squared. So we need the derivative here. Well, this is x to the minus 1. So f prime of x is minus x to the minus 2. Fine. I wrote that down wrong. It's 1 plus. Oops, sorry. I already got the 1 plus. The derivative is, I'm going to write minus 1 over x squared. Yeah. Okay. So that's the r of x, the distance from the curve to the axis you're rotating around, and then 1 plus the derivative squared. Okay, so let me just make that pretty. As 1 plus 1 over x to the 4th dx. Okay. Now, we're trying to work this out. I mean, I don't even know if I've tried, but we don't need to do that. We don't need to do that. Okay? Now, how do you, I want to find an integral that's less than that. Right? So I want to find, so this is going to be greater than something else. So I'm just going to bring down the 2 pi and keep the integral from 1 to infinity, and I'm going to keep the 1 over x as well. So I kept all this stuff the same. I want to talk about that expression. Okay? So what I'm trying to do here, I mean, for example, if you knew that A was bigger than B, say, bigger than or equal to, and I had, 2A plus 7, right? What happens to this expression if I replace A with B? Well, if A is bigger than B and I replace A with B, that means I'm going to get smaller, assuming everything else is the same, right? That's what I'm trying to argue here. Or, what if I said A was bigger than or equal to 6? Well, if I replace A with 6, that's going to be less than or equal to that, right? Because if A is 6, they're equal, but if A is 7, that's going to be bigger than that. So whenever you have an expression and you replace, one of the elements with something is smaller, you're going to get smaller, okay? That's what I want to do here. I left everything else the same, but let's look at this radical right here. Okay? X is at least 1. Do you agree that that right there, the square root, well, here, let me just change it to this. Do you agree that 1 plus 1 over x to the 4th will always be bigger than or equal to 1? So if you think about what I'm arguing here, 1's the same, I'm replacing that with 0. This is always bigger than or equal to 0, isn't it? Right? So what I'm saying is, start with this expression, leave the 1 alone. That is always bigger than or equal to 0. I'm replacing it with 0. That is always bigger than or equal to 0, and so that's going to be true. And if I put this positive square root on it, that's still going to be true too. So if I replace this entire expression with 1, I'm going to get smaller because I replace this with something that's, I replace this with something that is always less than or equal to that radical. So you don't actually have to work this out, okay? I replace some messy part of it with something I know is smaller. Well, let's look at what we have here, okay? 2 pi integral 1 to infinity 1 over x dx. Use that p theorem that I used a second ago, right? This is p equals 1. I'm going from 1 to infinity, right? Just like the theorem said, and p is 1. Well, what did the theorem say about the integral from 1 to infinity of 1 over x to the p when p was 1? That integral diverges. So this integral diverges. So that's blowing up. I'm multiplying by 2 pi. It's even worse. That diverges. Right? Well, this integral diverges, and this integral is bigger than that. That goes back to my f and g picture I had a second ago. This is the smaller integral, and it goes to infinity. This is bigger than that, which means this goes to infinity. Right? So this integral diverges as well. Okay? So what does that tell me about the surface area? Okay? So again, write in your notes, this integral diverges by that result, that number 52 up above. This integral also diverges, but that was the surface area. So it has an infinite surface area. So think about what we got for volume. This Gabriel's horn has finite volume, so you can fill up the inside with paint, but as an infinite surface area, you can't paint the outside. So that's what this is telling us. Now you have to be careful when you're working with infinite things going from 1 to infinity. They don't work the same as finite things, so don't try to extrapolate finite to the infinite. You get weird stuff like this. Okay, so that does it for that section.